Welcome to Yaka Digital Network. Take a look at this map of a Ugandan tea estate. We have a straight fence, represented by the linear equation y equals 2x minus 3, intersecting a winding river, which follows the quadratic curve y equals x squared minus 4x plus 5. To find the exact coordinates where the fence crosses the river, we need to solve these nonlinear simultaneous equations. In this split view, watch the math mirror the map. To calculate the intersection points, we use the substitution method. Since both paths are equal to y, we set them directly equal to each other. Rearranging this expression to bring all terms to one side gives us a single quadratic equation, x squared minus 6x plus 8 equals 0. Before factorizing, we can predict the nature of these intersection points using the discriminant formula, b squared minus 4ac. Since our result here is positive 4, we know we are looking for two distinct points on the map. Factoring our equation gives us x minus 2 times x minus 4 equals 0, confirming our x-coordinates are 2 and 4. Notice this warning on the screen. It is a common mistake in exams to find these x values and immediately move to the next question. We are calculating physical coordinates on a map, which require both an x and a y value. To get our y-coordinates, we substitute 2 and 4 back into the simpler linear equation, y equals 2x minus 3. When x is 2, y is 1. When x is 4, y is 5. We now have our complete coordinate pairs. Solving simultaneous equations is the precise mathematical method used to find the exact locations where two distinct paths collide. While equations isolate specific intersection points, inequalities help us identify entire ranges of values, like determining all the acreage that sits north of a specific boundary line. Look at this whiteboard display. A standard UNEB question will ask you to find the range of values where a quadratic expression, like x squared minus 2x minus 8, is strictly greater than 0. The first step is to temporarily treat this expression as an equation. Watch as the greater than symbol becomes an equal sign, allowing us to factor the expression into x minus 4 times x plus 2 equals 0. Solving this gives us x equals 4 and x equals negative 2. These are our critical points. These critical points act as the absolute boundaries for our problem, splitting the number line into distinct regions where the underlying math will test either positive or negative. Here on this graph, we plot those critical points at negative 2 and positive 4 on the x-axis. Because the x squared term in our original expression is positive, we sketch an upward opening parabola through these 2 points. Take a moment to look at this curve. Can you visually identify which sections of the parabola sit strictly above the horizontal axis? The sections greater than 0 are the 2 outer arms of the curve, highlighted here in green. Looking at the shaded regions on the x-axis, these green arms correspond to all x values less than negative 2 and all x values greater than 4. That is your final range. We verify this by testing the middle region. If we plug x equals 0 into our original expression, the result is negative 8. Since negative 8 is not greater than 0, the test fails. The middle section is excluded. Sketching the parabola provides a visual check, helping to catch the common sign errors that often occur when working with abstract numbers alone. Look at this exam strategy graphic showing a rational inequality with variables in the denominator. You must never multiply both sides by the denominator. Because we do not know if x minus 1 is positive or negative, multiplying by it could flip the inequality sign. Instead, the correct method is to isolate the critical points by setting the numerator equal to 0 and the denominator equal to 0 separately. You then use these points to test your intervals on a number line. Let's review the core rules to secure maximum marks. For simultaneous equations, first substitute, then factorize, and always remember to solve for y. For quadratic inequalities, find your roots, physically sketch the parabola, and read the correct regions directly from the graph. As we saw earlier, the discriminant formula allows you to prove the nature of these intersections. Set it equal to 0 to prove a line is tangent to a curve, or show it is less than 0 to prove an expression stays entirely above the x-axis. Mastering these 3 specific frameworks makes solving complex algebra questions a structured process, leading to more consistent results in your UNEB exams. To put these frameworks into practice and access comprehensive class materials, visit us at Yaka Digital Network.